Let's get started again. Let me pull your textbook back up if I can find it. I thought I had it, but I apparently don't. Let me see. Sorry for the lag. Yeah, here we go. Now, rationalizing denominators, I've already done that. Okay, I got a little ahead of myself, but this is what we did earlier. We'll just refresh example 8. 2 radical 3 over 3 radical 10. Notice we want to get rid of the radical 10. So now you can't really mess with the 3. All you do. Here's another way to look at it. You multiply by 1. But we're writing 1 in sort of a weird form. We're writing 1 as radical 10 over radical 10. And remember how it said we don't really need the minus signs by these 2 radical 10s here and here. Anyway. So, because they cancel anyway. Now, by associativity, we can multiply this radical 10 here and this radical 10 here and just get plain liberated 10. And 3 times plain 10 is 30. Now, up here, hey, look, that's what we wanted. We got a clean denominator. Now, up here, we just get what we get. Radical 3 times radical 10 is radical 30. And times 2 is just, well, is what it is. It's 2 radical 30 up here. Now, can we reduce? Maybe, sometimes. In this case, yes. 2 over 30 is 1 understood up here. So that's an invisible 1 times a direct radical 30 not 30 now. It's 15 because 2 goes into 30 15 times. So we cancel the 2, get an invisible 1. We cancel the 30 and get a 15 that we can see, right? And the radical 30 just stays put. Okay, right here. And on number 8, multiply top and bottom by, radical 2. You're multiplying by radical 2 over radical 2, in other words. But you'll stick a radical 2 at the top and at the bottom. You'll get 12 radical 6 over 2. That's 6 radical 6. And here's how to go about it verbally. Example 9. Now, this time it's more convoluted. You got to do a thing called the conjugate. You negate the middle. And here you can't wish the negatives away, right? So you multiply by 1 minus radical 5, the conjugate of the 1 plus radical 5. But what you do at the bottom, you got to do at the top because you want to multiply by 1 here and here. Now, you do distributive FOIL down here. Remember the middles cancel like we talked about earlier by FOIL. You'll end up with negative 4 because you do FOIL. You'll get 1 minus rad 5 plus rad 5. They cancel. And then you'll finally get, minus regular 5. And 1 minus regular 5 is negative 4 here. And now, what about this? Now, you see this negative 4, you can divide each of these 2 terms up here by the negative 4 down here. Pos 4 divided by negative 4 is negative 1 here. And so you get negative 1 plus radical 5. How come? Well, again, why the plus radical 5? Let me back up and do it again. Pos 4 over neg 4 is neg 1. And then neg 4 rad 5 over neg 4 is plus 1 rad 5. So we get plus 1 rad 5 here. So you get negative 1 plus radical 5. Sure, you do. It's just you can also write it as radical 5 minus 1 right here. And this one, you conjugate this one, you multiply by 2 minus radical 3 over 2 plus radical 3. Sorry. No. You multiply by 2 minus radical 3 over itself, 2 minus radical 3. So you multiply by 1, but you write it as 2 minus rad 3 over the same 2 minus rad 3. You'll end up with 7 parentheses up top, parentheses after the 7, and put 2 minus rad 3 inside the set of parentheses. Close off the parentheses. And down here, you'll have, what will you have? You'll have 1. But you can ignore the denominator, it's 1. So your final answer would just be 7 parentheses 2 minus rad 3. Now we'll move on to rational roots. Now the principal nth root, you remember how when we take the roots of 25, technically there's a 5 and a negative 5 when we do the principal. When we do the principal square root is positive 5, The extraneous square root is negative 5, because both positive and negative 5, if you put them in parentheses, they'll square to 25, right? But the principal one is positive 5, the principal nth root. If a is a real number with at least one nth root, then the principal nth root of a is written, the nth root of a is the number with the same sign of a. It's the number with the same sign of a. So the fifth root of neg 32 is neg 2. It has the same sign. If you all ever take complex analysis or complex variables when you get older, there'll be 5 roots, but negative 2 is our principal, and we're not going to do that right now. We're just going to do neg 2 in this class. We're not going to do the others. All we care about is neg 2. Why is it neg 2? Because neg 2 to the 5th power is neg 32. The 5th root of neg 32 is neg 2, because negative 2 times itself 5 times is neg 32. That's what it means to take the 5th root. Now part B, you can't do much with these, but if you gel them together, you'll get something that looks even worse. 4 times 1024 here is 4096, but the 4th root of that is, interestingly, 8. That's pretty, right? And if you do 8 to the 4th, that may not be obvious, but you'll get 4096. Part C is right here. They're kind of all jingled up. Part C is right here. The cube root of, the negative sign just stands out. It's just there. The cube root of 8 is 2. And remember, here's how we do this. You do 6 divided by 3. That's 2. You divide the power by the index, guys, from Algebra 2. So 6 divided by 3 is 2, so it's x to the 2 power. You divide whatever power is here by whatever index is here, and that's 2. And if it's not divisible, if it's smaller, you can't do anything about it. You just leave it. If it's bigger, like you take out what you can. Like if that were x to the 7th, you'd separate that x off, and you'd take this x to the 6th out as x squared, you leave an x in there or something. Now the cube root of 1, I'll show you in a minute. That was kind of vague. I'll show you what I meant here in a minute. Now the cube root of 125 is 5. So there you go. This one's pretty, right? Everything cleaned up real nicely. Let me show you one what I was talking about a second ago. What if it didn't clean up real nice like this? You can make it work. Just depending. Home, insert, equation, lately I've been having to go to the draw tool, which is kind of it's irritating, but I'll ink it. So let's say that I want to do the 5th root of let's say 32. That's 2, by the way. But no, I'm going to do something more interesting than that. Let's say I do x to the... Let's say I put x to the 50 here. Let's say I put y to the 51 here. And let's say that I put z as in Zimbabwe. And let's say that I put 50. Well, that's kind of sloppy, isn't it? Whoa. Uh-oh. I didn't want that. No. Oh, let me scroll up. Sorry, guys. That was a disaster. Hold on. Is there any way I can... Well, zoom out. Okay. Z, never mind. I'm sorry I asked. So let's just do z to the power of... Let's just do z to the power of 52. Okay. And where can I get out of here? Get me out of here. Okay. So let's see. So let me try to zoom out of here. Oh no. Zoom out. And okay. Well, let me insert. Oh no. Okay, thank goodness. Exit drawing. So let's exit drawing and let's do z to the power of 52. That was a nightmare. Okay. And let's insert that. So what this is going to be, and my radical looks all clumsy, but y'all get the idea. No, z to the power of 52. So I got the fifth root of all this stuff. Now, and sorry my radical got a little fragmented there. Now the fifth root of 30, now let me copy and paste maybe the first part of this. So now let me hit Control V. So I've got y to the 51, z to the 52, and I've got 3 minutes to play with. Let me get rid of this. It's kind of wonky. So there's the pretty version. So I've got this. Now I want to tinker with it. So let me hit Control C. And what I want to do with it, now I want 5 is my index, so I want multiples of 5. Will 5 go into 50? Yes. Will 5 go into 51 cleanly? No. But if I chunk y off as 51, 51 is 50 plus 1. So it's y to the 50 times y. And 52 would be y, for z would be z to the 50th times z to the 2, like that. Y'all agree? So I just chunk z to the 52 is z to the 50 times z squared. So, well, what can I take out? The fifth root of 32 is 2. And now for x, I do 50 divided by 5 is 10. For y, I do the same thing. It's 10. For z, I do the same thing. It's 10. But now I still need my fifth root. But I'm going to most stuff has came out, but a few things are still left in there. So for my fifth root, my z squared is still in there, right? My z to the 50th is gone. My y to the 1 is still in there, but the 50 powers are all gone. The 32 is gone. So all that's left in there is just, and let me put a little space. Well, and so there we go. So my final answer is 2 times x to the 10th times y to the 10th times z to the 10th times the fifth root of yz to the 5th. Maybe too much space. There we go. But yeah. That may have been good. Let me do a little like this. Yeah, there we go. But yeah, I put that dot. You don't have to put that dot there. I just did for neatness. The dot's not really necessary. But, so 50 divided by 5 is 10 for each of these, right? And you'll notice, yeah, that's basically the idea. If I go back and make this, let's say 61 for y, well, I would have to do that here. Well, that would just be 60 plus 1. Now, 60 divided by 5, be careful, that's 12, right? But otherwise, nothing else changes, right? That's how you do it. It's kind of like quotient remainder, you know? But yeah, it's not so bad, right? So I'll see y'all in the next video.